In this video, we're going to be addressing the basics of linear equations. This is technically assumed knowledge for the course. These are the MTE modules 4 and 5. And a lot of us have dealt with this material extensively in high school. But today, I'm going to kind of reframe a lot of this information in the context of a real-world problem. And in this video, we're only going to solve one problem. So all we set out to do today is compute, analyze, and interpret the rate of change in the context of a real-world problem. In 2012, Congress gave Dominion Power the green light to dump coal ash into the James River. In 2013, Dominion dumped 543 pounds of coal ash into the river and dumped a constant amount of ash into the river each year. In 2017, there was 1,103 pounds of coal ash in their dump site. At this rate, how much coal ash would be in the river in 2025? Pause the video and work this out on your own. You don't have to use linear equations. You don't have to use any crazy math for this at all. Use your intuition and see if you can come up with an answer. If you came up with 2,223 pounds, you did this correctly. And you may not have known it, but you were technically utilizing linear equations in solving this. If you didn't come up with this, that's okay. We're going to walk through exactly how you arrived at this answer. So what do we need to know? In order to answer this question, what are some of the things that we actually needed to determine? First, we needed to know the rate at which Dominion dumped coal ash per year. Once we found this, we can derive an equation to model the amount of coal ash in the river at any given year. So if you gave me a year, I could tell you how much coal ash there is. We have an independent variable, t, which we will define to be the number of years since Dominion started dumping coal ash. So if t is equal to like 4, that's 2016 because they started dumping in 2012. So it's 4 years after they started dumping. And our dependent variable, a of t, that's the amount of coal ash in the river. I know it seems like we're just kind of rolling out fancy math on top of this very intuitive thing, but really all we're doing is we're giving definition to these things. So first we're going to find the rate. So if I think of the initial dump as year 0, the number of years after 2012 in 2012 is 0, I can make that my x value, my t value, my independent variable, and the amount of coal ash in the river is going to be my dependent variable. So that was 543. So I've got one coordinate pair there. In the original problem, I told you that in 2016, there were 1,103 pounds of coal ash. So 4 years after they started dumping, there were 1,103 pounds of coal ash. Now, I want to know the rate. Since we had this word constant, that means that we're dumping the same amount every year. So if I think of this as a collection of ordered pairs, I'm going from 0 to 4, and what the y values are doing is they're going on a ride. I'm adding some number to them each and every time. That number, we'll call it m, which should be familiar, but you'll see where it comes from. That amount of pounds, right? It's just the same amount each and every time, so I can denote it with one variable. So ultimately what I'm doing is I'm taking 543, I'm adding m to it 4 times, m plus m plus m plus m, and I'm going to get 1,103 pounds. I dumped 4 times the same amount. I started with 543, and now I've got 1,103. So I could also write this as 543 plus 4m is going to be equal to 1,103. So I want to solve for m. So in order to do that, I'm going to start by subtracting 543 from both sides. And then I'm going to divide by 4. And that's going to tell me what my m value is. So now I get 560 over 4. Before I just go ahead and mash this number out, let's look at what we're saying here. What we're saying is in 4 years, 560 pounds have been dumped. So that's 560 pounds per 4 years. If I actually do this division, what it's going to do is tell me the amount of coal ash dumped per 1 year, which is what I really want. And so I get 140. Now, what does that mean? What that means is every year I'm adding 140 pounds of coal ash into the river, okay? So that's going to be my rate. And what we see is that as I move up one x value, I move to the right one x value, I'm moving up 140 y values. M is going to signify the number of pounds dumped per year. And now let's interpret M. What does this mean in context? So we're going to start in the year 2012, or 2013, I'm sorry. Geez, I got the whole thing wrong. So 2013, we've got 543 pounds dumped. So T at 0, that's the year we started, got 543 pounds. Next, in 2014, I'm going to throw 140 pounds on top of the pile, which means I've got 683 pounds now. Then 2015, I'm going to throw another 140 on top. And each and every year, I'm just going to keep adding 140. And I already knew in 2017 that there was going to be 1,103. Okay, so that's what M means. Effectively, it's how much was in the bed of the truck when it dumped into the river. So let's think more about this. What M represents here is the amount of coal ash dumped each year. And we could also think of this as the rate at which A of T changes with respect to T. Now 2025, that was what the question was initially asking. We wanted to know how many pounds of coal ash there was in the river, particularly in 2025. So now what we're basically saying is we want to find what happens when T is equal to 12. So what that's going to mean is I'm going to start with 543 pounds, and I'm going to add 140 pounds 12 times. If I want to write this out the long way, I could do it like that. But surely I want a more succinct way to do it. If I'm going to add 12 140s, I can think of multiplication as repeated addition. That's really just going to be 543 plus 140 times 12. And to get the short answer of the question, I get 2,223. Some of you certainly got this answer without doing nearly as much algebraic or arithmetic setup. But you were doing this without doing this, if that makes sense. You were doing algebra without algebra. Now, let's extend the question here. Most math students can answer a question that's assigned to them. Really good math students can answer every question assigned to them. And great math students know how to ask a bigger question based on what was assigned to them. So let's ask a bigger question here. Can we come up with a way to predict the amount of coal ash in the James River for any given year? Any year. You give me a year, I can make a prediction about how much coal ash there is. Sure, that doesn't seem like a tall order at all. Let's start with just T. So if I start with T as some number of years, if I want to find out how much coal ash there is, I'm going to take 543 and I'm going to add T 140s. If I think of multiplication as repeated addition, what I'm really just saying here is 543 plus 140t. And now I've got an equation. My initial value, that's what I started with. I started with 543. That's just going to be my constant. And the rate of change is going to be attached to the variable by multiplication. It's almost like we've set up an equation that looks kind of like y equals mx plus b. There's your b value. There's your m value. It's almost like this isn't made up. So now let's talk about the rate of change formula. Given any two coordinate pairs, can we find the rate of change between them? Well, yeah, if we set this up the same way that we did at the beginning of our problem, if I have some coordinate pair, what I'm going to have is some number of coordinates between them, and I'm adding m each and every time. So there's going to be an x2 minus x1 number of m's added to y1 to get to y2. So I'm going to take y1, I'm going to add x2 minus x1 m's to it, and I'm going to get y2. So I'm going to solve for m, because that's what I want to find here. So I'm going to start by subtracting y1 from both sides. And then x2 minus x1 is just a number. Why don't I just divide both sides by it? Gasp. It's the slope formula. We didn't do any magic. There was no super highfalutin math that we did here. We just found the number of coordinate pairs in between the two values we were given, the two pairs that we were given, and that was our x2 minus x1 coordinate pairs. And then I just divided the difference of the y's by that. This is the slope formula. So now, let's summarize everything. Rate of change. What is it? The rate of change of a function f of x tells us, tells us the rate at which f of x changes with respect to x. The way I calculate it is by using our slope formula that we've used time and time again. And why is this important? Well, if I consider setting up a model, I can set it up using initial value added to my rate of change times my independent variable to get my output value. Now, I understand we're used to saying y equals mx plus b, but this is obviously the same thing. Okay. So now what we're going to do is talk about a graphical interpretation of linear equations. We're going to get into this much more thoroughly in the next video, well, the next lesson, 2.2. So vertical intercept, that's going to be our y, our y-intercept. You could think of it like that. Okay. Slope of the line tells us how far to rise and run to get to the next point, right? We think of our change in y as our rise, our change in x as our run. So now let's suppose I have these two pieces of information, and I want to write the equation of the linear function that satisfies these properties. I have that f of 3 is equal to -1, and I have that f of 6 is equal to -3. Remember, this is my domain value, so you could think of this as my x. What I'm saying here is when x equals 3, this is my output value, y equals -1. So I can organize this into a coordinate pair, 3, -1. Same thing here. I'm saying, okay, well, there's another point when the x value is 6, my y value is equal to -3. So what I really want is, what's the line passing through these 2 points? Okay. So it's a linear equation. Begin with the end in mind. It's always going to be mx plus b. I'm asking for a linear function, so it's going to have to look like that. Now what I need to do is just find the m, and I need to find the b. So first we're going to compute the slope. We're going to use our slope formula for that. Here's our one coordinate pair, 3, -1. Here's our other coordinate pair, 6, 3, or I'm sorry, 6, -3. Sorry about that. I don't know why the animations didn't stay there. And this is what the line's going to be doing. Okay, it's going to be passing through these things. Now, again, this is just having the answer in front of us, but that's okay. Think of it like we were given the line and we want to compute this slope. So let's do it. Let's compute this slope. So I've got my two coordinate pairs, and I'm going to set up my slope formula. Sorry about that. So I'm going to set up my, I've got my coordinate pairs, there they are. And now I'm going to set up my slope formula. So let's do it. I've got m is equal to, so 3, -1, 6, -3. Sorry, I didn't realize how clunky these animations were. y2 minus y1. Divided by x2, consistency is important, minus x1. So -3 minus -1, that's going to turn into plus a positive. That's going to be a -2 over 6 minus 3, that's 3. So m is equal to -2/3. Okay, so I've got my m value. And now I need the b value. So how do I find the b value? Well, I mean, we know that the b value is going to be the y-intercept, so if I really wanted to, I could just look at the picture and go, oh, cool, b is going to be equal to 1. But let's pretend we didn't have this picture in front of us. Well, we've got our coordinate pairs, and now what I'm going to do is plug in this coordinate pair. So here I know that x is equal to 3 and y is equal to -1. So I'm just going to go ahead and plug the 3 into this equation. I'm going to plug the -1 into this equation, and now I'm going to solve for b. So the 3's cancel, and I get -1 is equal to -2 plus b. So now I'm going to go ahead and add 2 to both sides, and I get b is equal to 1, which gives me this final equation here. Now again, if we had looked at the picture, we could have just seen that b was equal to 1 because that was where the y-intercept was. But let's suppose we didn't have that. These are the basic pieces of information that you need about linear functions. We started from scratch, and we built kind of the theory of what rate of change is, what slope is, what does it mean when it's positive or negative, things to that effect. And then we kind of started sculpting a particular equation out of it. So that was really the main thing I needed you to take away from this video.